Welcome everybody. Today we will start with section 5.5 collision model. As we learned before in section 5.4, for any reaction to occur, the particles have to collide in a proper orientations with sufficient amount of energy. So these are the three things that the reactant particles must achieve in order to produce products. In order to increase the rate of reactions or to increase the probability of having a proper orientation, this thing is achieved by increasing the concentration of particles. So the more particles, you increase the rate of collisions, and that's why you're increasing the probability for having a proper orientation. We can increase the collision rate in terms of temperature or adding a catalyst or using high surface area of reacting particles like powder reactions are way better than the solid or blocks of reactants. In our case, we're going to study the effect of temperature on the collision of reactions in terms of a graph, and this graph is called Maxwell Boltzmann distribution, and it refers to the two scientists who postulated this idea. In our case, we can see we have a graph. The y-axis is labeled to the fraction of molecules, and the x-axis represents the kinetic energy. As we can see, we have two curves. We have curve 1 and curve 2. Let's call it T1 and T2. The difference between these two curves is the temperature. The one that is shifted to the left and it's narrow, we can notice that it's done at lower temperature. The broader one, as we can see in the red one, as in the red color, the shorter that is shifted to the right a little bit is done at higher temperature. So generally speaking, if you want to draw any Boltzmann distribution for a cold temperature, we can draw it in terms of a narrow part. And if we want to draw another one that is done at higher temperature, it's a broad in addition to it's shifted to the right a little bit. And this one is done at higher temperature, and this one here is done at low temperature. One more thing that we can deduce, if we look at the fraction of molecules here, the greatest number of molecules, they have this amount of energy. So we can say that this energy represents the most probable energy, which means that the most of the particles have this amount of energy. As we can see, we have one more thing to discuss. We can notice that there's a dashed line in here, and the dashed line represents the activation energy. Okay, so this one represents the activation energy. And for the guys who don't know what activation energy is, it's the minimum amount of energy needed to initiate the reaction. Okay, so in order to start the reactions, you have to supply the system with amount of energy in its minimum case, and this is the activation energy. The fun fact about this activation energy, you can see that all of these, I just want to erase all this stuff in here, all of this amount of energy in here, all of these particles in here, they do not, or they are unable to do the reaction. And that's because their energy is less than the activation. Reacting particles should have energy greater than the activation in order to overcome the wall of energy, and that's why start the reaction. So if the reacting particles have energy that is less than the activation, no reaction will take place, but here it will take place. Where do we find the particles with energy greater or less than? So the shaded area in here represents the reacting particles with the energy greater than the activation. So we can see that this is the shaded area in here represent the particles that are able to react. But the particles in this area, they just collide with each other, but without sufficient amount of energy. So they're reacting particles have a less amount of energy than the activation, and that's why the particles in this area are not able to react. Okay, now let's study something else. As we mentioned before, we have two temperatures as we have two curves. The red curve represents a greater shaded area than the blue area. At higher temperature, the fraction of particles, the number of reacting particles with energy greater than the activation energy will increase. So that's why you have more shaded area. Okay. So the shaded area at that point represents the fraction or the portion of particles with energy greater than the activation energy. What happened to the particles if they have a lot of kinetic energy? The higher kinetic energy leads to increase the collisions, and increasing the collisions leads to increase the proper orientations of these collisions. You're increasing the probability for having a proper orientation in addition to sufficient amount of energy. And that's why at the end, the rate of reaction will increase. So the rate of reaction increases as a result of increasing the temperature, because the temperature leads to increase the fraction of the particles with energy greater than the activation energy increase, and that's why the rate of reaction increases. If you look at this guy in here, he is just like applying amount of energy. He's doing some energy in order to lead the ball to flow simultaneously. And at that point, you are going to supply your system with amount of energy in order to move the ball upward and then go up, downward. So this is the same as the activation energy. You need to supply the system with amount of energy, and then it completes its way. All right, guys. If you have any questions, you can ask me in the comments below, or you can send me an email. Have a nice day.